So we're going to consider a new example, and also just as in the last one that we attempted, we're gonna just keep it generic. Probability of some event A is equal to 0.5, 50-50, half. Probability of event B is 0.2 or 20%, but we're also given the information that the two events are independent. So it helps you to be less generic. Let's make up a quick little scenario that we can think of for this. And so let's actually imagine that we're going to randomly assign Americans who volunteer to see whether garlic is a good prevention for COVID. And to be really sure, and actually this is sort of a research design issue, we actually, rather than giving some garlic and giving some none, we might like take garlic supplement and put in a pill and give the others a placebo, and we'll say that A is the event of being given or getting garlic, taking garlic, right? Maybe we say that treatment is they take garlic every day for the period of the study, over the course of a year, or we give it to them once a week, whatever we are testing out. And then there were people that were claiming that garlic would help prevent COVID at one point. It's not true. It doesn't seem to be true. There's a lot of evidence that garlic is good for many things and might kill certain bacteria, but it doesn't seem to be actually, at least scientifically, established to be any prevention against COVID. And so then let's let B be. I should have said take garlic, because I'm gonna. Let me say. I'll say contract instead of get again. Contract COVID-19. And let's assume, over the course over the course of, let's say, a year. And so that seems reasonable. I think officially we have somewhere over 30 million. It's definitely at least 2 times the number who are confirmed cases. So I think that it would not be unreasonable in retrospect to think that over the course of a year, take a random person and there's a 20% chance that over the course of the year they contract COVID. So here, this is kind of an experimental setting, right, where we're taking a bunch of subjects, half get garlic, half don't. We are essentially flipping a coin to determine who gets garlic and who doesn't. And we're envisioning, because we actually know that garlic does not prevent COVID. And so, since it's a blind test experiment and people don't know what they got, you can imagine that it could be an issue. If we knew and I was really confident that garlic would help prevent it, then maybe I'll take more risks. And so then maybe it'll look like taking garlic actually increases your chance of getting COVID-19. And so we won't let people know whether they're getting it or not. And we might even not tell them what the treatment is or what it's for. Okay, so, we can actually, the way we can think about, if you like, the visual of a Venn diagram here, because they're independent, and let's actually imagine, let's look at the, right down the middle. We'll let the coin flip, essentially, the heads, tails, whether you're getting garlic. We'll let the one on the left, doesn't matter, be A, and the one on the right be A complement. And then here's B. The 20% of outcomes are going to be ones that get COVID within the year, and we'll call that B. Everything inside that oval is B. Everything outside is B complement. So actually, maybe I should actually write B, as long as we recognize we're talking about on both sides of the line. That's B, and then outside is B complement. Okay. So just to be clear, right? Oh, here this red area is B complement, right? And B is what's inside, right? Okay. If that's helpful. Notice, you can actually tell by the way, I've done an okay job of doing it, that because they're independent, the visual is attempting to show, like, if 20% of the entire, the entire rectangle, the entire exhaustive set of things that can happen, that, oval that is the getting COVID, if that's about 20% of the entire rectangle, then it should also be the case that when we constrain our vision to just that those who have garlic, the half of the oval that's on the left side there, the ratio basically of the portion of the garlic eaters who contract COVID, right? The ratio of what proportion of A is the intersection between B and A should be the same as the proportion of a complement that is the intersection between B and a complement, right? So knowing that you're in one half of the garlic eater half or the non-garlic eater half is not telling you whether you're going to get COVID or not, because that treatment is not actually helping. So you can imagine, a scenario where garlic was helping, where it was maybe some other drug that was helping a prophylactic prevention of COVID, and then in that case maybe what you'd see is that the representation, we might make it smaller on the left side instead of what we had, but we're not. It's evenly in each. Okay, that's a long-winded way to give you potentially a kind of a helpful mnemonic. But let's use the rules that we have for calculating the first one, which is the probability of the union of A and B, so that probability of A or B. What is that? What is that in terms of the Venn diagram? It's it's like picking someone at random. What's the probability? So and the universe of people I'm interested in are the people that are in this study, right? So of those in the study, what's the probability that so you'd say you're in the study, what's the probability that you're someone who either gets the garlic treatment or contracts COVID, or both? And these are independent, so this means we're talking about being in the A set or in the B set, right? And so what does that look like? Well, we know, you should be getting used to this now if you've been going through them. This is equal to the probability of A plus the probability of B. Is that it? No, because they're not mutually exclusive. You have that overlap, so don't forget to subtract the probability of A intersect B, right? So what is that going to be? Oh, well, let's see. We're given part of it. We're given probability of A is 0.5 plus the probability of B is 0.2. But we weren't given the probability of A intersect B. So what do? Well, we have some information. We know these are independent events. When you have two independent events, then the probability of their intersection, the probability that both happen, is the probability of one times the probability of the other, right? We get to do that simple multiplication without any conditional because these are independent, right? So that's going to be equal to 0.7 minus 0.5 times 0.2, which is equal to 0.10, right? So that's equal to 0.7 minus 0.1, which is 0.6, or 60%. 60% if you like percentages. Okay. And I will stop it there and break this up, I think.